In this video, I'll talk about the hydrolysis of nitriles to carboxylic acid. The hydrolysis of nitriles can be done under acidic conditions and under basic conditions, so it's really your preference how you want to be doing it. However, the product can be slightly different when you're doing it under acidic condition versus the basic conditions. Under acidic conditions, you eventually make a carboxylic acid, and since it's being done under acidic condition, it makes an OH, the carboxylic acid. But if you're doing it under basic conditions, you're not going to be exactly getting the carboxylic acid, but rather you will be getting a carboxylate ion, because remember, this is being done under basic condition. But you can certainly go ahead and get that converted to an acid if you just do an acid workup at the end. So the mechanism can be slightly different, and regardless whether you're doing it under acidic condition or a basic condition, the hydrolysis of nitriles goes through an amide. So you first make the amide, and then eventually amide gets hydrolyzed to an amine, to an acid rather. So if I'm doing, suppose this under acidic condition, so the first thing I want to do under acidic condition is go ahead and protonate. Remember, anytime you're doing something under acidic condition, you don't want to be creating a strong base during the mechanism. That would be a big no. So I want to go ahead and protonate that nitrogen, and when I go ahead and protonate that nitrogen, I get nitrogen here with a positive charge. Now I can have the water acting as a nucleophile, and this water, oxygen, is going to go ahead and attack that carbon here, and I'll go ahead and break this one of the pi bonds on that. So in doing so, I get only a double bond left with the nitrogen of the carbon. So something like that. And then I have an oxygen kind of connected to the carbon now, but now you get a positive charge. So I got to go ahead and get rid of this positive charge. And to get rid of that positive charge, I can just do a proton transfer. Now, books show the proton transfer just in acid-base reactions different ways, and it's fine most of the times because you don't want to be rewriting things over and over. But I'll just kind of go the longer way. So the water I got in the solution can go back and grab this proton, so that now I have, I'm just going to copy this down here. So this oxygen already has one lone pair. Once it breaks that bond, so in the next step, I can go ahead and use the acid again to protonate that nitrogen. So I'm going to go ahead and protonate that nitrogen, because remember, any step in the process, I do not want to be creating a strong base. And I want to go ahead and protonate this. So when I go ahead and protonate this, I'm just going to go ahead and copy this down. I have nitrogen with a positive charge here now, and then I can go ahead and reform the pi bond here, and then that pi bond breaks to make the NH2. So this process will eventually make carbon with an oxygen double bond there. Oxygen gets a positive charge, and now you got the nitrogen with a lone pair and two hydrogens connected. So we're kind of on the way to amide in this particular case. Then in the next step, I can run another proton transfer reaction because I don't want to leave that protonated oxygen up there. So I can do a proton transfer where you can use water. So when I use water to do the proton transfer, I can go ahead and grab the proton from here, and that would make, just going to copy this, put it right here. I make that, and then since this is an amide, I want to go ahead. So I actually made the amide in this particular step in here, and then this kind of gets stuck in here where it's kind of going back and forth with the amide and the protonated oxygen in this particular case. So if you want to go ahead and further hydrolyze the amide eventually to an acid, I can start from this step here where I can go ahead and use water to go ahead and protonate this, and then this comes out here. So this kind of gets a little bit tricky, so you want to make sure you kind of keep track of what's really happening in terms of the arrows and what's being made. So I get an OH there. I get a new hydrogen or water molecule get connected, and then I get the NH2 there, still kind of hanging in there. So now I want to go ahead and run in a proton transfer here. So when you're doing a proton transfer, I can literally, if I don't want to be like rewriting things over and over, I can have one of these transferred from that oxygen that gets the positive charge transferred onto this nitrogen, or I can use the help of water and do that in multiple steps. But you know, typically you should be okay just writing the proton transfer at this point. And when that happens, I can say, okay, I'm going to lose one of the hydrogens from that oxygen, and then I'm going to go ahead and install one of the with that particular hydrogen onto that nitrogen, so that nitrogen gets the positive charge. Because the whole point is I want to make sure I'm making a good leaving group out of that nitrogen. Now that's in a good leaving group, I can go ahead and use any one of those lone pairs from the oxygens to kind of make the pi bond. Doesn't really matter, so I can go ahead and make the pi bond here, and that gets knocked out. So you lose ammonia here, because that's in a good leaving group. NH2 minus is typically in a bad leaving group, but that does, you can leave that if you doing this under basic condition, but under acidic condition, I want to make sure I protonate that. So I lose ammonia, and in the process, I have now something like this. So acid kind of made already, and then I want to go ahead and just use the water again to remove this proton from here. But at the end of the day, the most important things that you want to kind of memorize from the hydrolysis, that if you're doing the hydrolysis under acidic condition, you make the acid, it does go through the formation of an amide, and eventually sometimes you would also see the reactions or the hydrolysis of amide, which actually makes the acid itself, but the hydrolysis of nitrile, which eventually makes the acid, but it goes through the formation of an amide. If you're doing this under basic condition, you wouldn't make that. So how would the things kind of look different under basic conditions? So suppose I have this generic nitrile here, and under basic condition now, I'm not going to be able to protonate anything here, but rather I'm going to go ahead and do the direct attack on that carbon, breaks that bond here. So I get a negative charge now. So I get an OH installed here. I get a nitrogen with a negative charge. And then I can go ahead and run in a proton transfer here using water. So when you're using base, which is the OH minus, which that technically means you're also going to have some sort of water in there, because you know, either you're making that base in water or something else, or maybe alcohol, but you can use that conjugate acid to go ahead and protonate this. As long as I don't create a positive charge where that positive charge is making a strong acid, I should be fine. So this is what it's going to look like. This got nitrogen with a double bond, and then I got one of the hydrogens installed there. Now I can have my second molecule of OH minus technically here. Now this can undergo a tautomerization. I'm not going to show the mechanism, where I'm just going to have a carbon with an oxygen here and a nitrogen here, because this is done under basic condition. You can show the mechanism where you can remove the proton from here, and you can add the proton here. That's using water and the OH minus, but you can just say it's in tautomerization that makes the amide now. Now then amide can be further hydrolyzed using the OH minus, where I can go ahead and attack directly onto that carbonyl carbon, and this breaks off here. And in the process, I get an O minus here, and I get OH installed, the new OH that we just got, the nucleophilic attack, and then I have the NH2 there. Okay, so then I can say that I'm going to go ahead and reform this pi bond even though you know the NH2 minus is not a good leaving group, but it can go ahead and leave because we're doing this under basic conditions. So you can go ahead and get rid of this to make the pi bond, and it's pushing, the NH2 minus is going to be being pushed by the reforming of that pi bond. And I can go ahead and use just the water here to make sure I protonate this. So when this kind of breaks off, I don't have to draw that too curvy. So this breaks off, and this comes out here to make that oxygen or the OH minus kind of go away. So you lose NH3 eventually, which is going to be in a gas. And I go ahead and make R acetyl bond O. And don't forget that OH there. So remember, this is being done under basic condition. I don't want to be leaving this with the protonated form of that acid, but rather the OH minus that you just have hanging out in the solution can go ahead and remove that proton and makes it a carboxylate ion. So that's really the only difference that you got. But you can certainly have an acid workup. So the acid workup is going to be separated from the actual reaction, and that acid workup will just make sure that you would protonate this oxygen at the end of the day. So you don't want to be leaving this not protonated. If you not using the acid workup, you can just leave it in the form of carboxylate. And that would be true whether you're doing the hydrolysis of like nitriles or amides or even the esters. If you do this, if you're doing a basic hydrolysis and not do or not follow up with the acid workup, you will just go ahead and end up with a carboxylate. And right, this is going to be your hydrolysis of nitriles.